Welcome to the second in a series of instructional videos focusing on the basics of analog synthesis. All of these videos so far have been geared toward those who are new to analog modular synthesis, and they all feature equipment by Pittsburgh Modular Synthesizers. In this video, we'll focus on the three waveforms generated by the oscillator and the synthesizer block module. We'll talk a bit about the basic properties of sound, and more importantly, we will talk and look at the harmonic content of each of the three waveforms, which is what distinguishes the sound of one waveform from another. I have patched out of the mix output from the synthesizer block directly into the mix 1 section of the M3 module because I wanted to bypass the filter, the envelope generator, and the voltage controlled amplifier. So we'll hear a constant tone as we look at these waveforms, and that is why I then have patched directly out of the mix 1 section back into the outs module, and I've also then taken an output into channel 1 of my USB PC oscilloscope. This will allow us to view on the computer monitor the shape of the waveform and switch over to the spectrum analyzer and look at the harmonic content of each waveform. We'll also talk about the basic properties of sound, of frequency, amplitude, and timbre. Talk about what those mean in relationship to the way a waveform sounds the way that it does. To better understand the process of sound synthesis, it's helpful to understand a few of the basic acoustic properties of sound. Depending on the discipline, the list of the properties of sound can range from 3 to 8. In this video, we'll focus on just 3 of the properties: frequency or pitch, amplitude or loudness, and timbre, or what we call color. When a string is bowed, plucked, or picked, a series of sound waves, that is, alternate areas of compression and rarefaction of air molecules, are set in motion that radiate out from the source. The string vibrates as a whole, and the rate at which the string vibrates determines its pitch, acoustically what we hear as the fundamental frequency. The volume of air molecules that are set in motion determines the amplitude or the loudness of the fundamental. At the same time the string vibrates as a whole, it vibrates in half, it vibrates in thirds, in fourths, etc., all the way out to the molecular level. The frequencies that these parts generate are known as partials, overtones, or harmonics. Generally, the smaller the part that's vibrating, the less air molecules are set in motion, the softer the tone that's generated, the softer the harmonic that you hear as part of the color of that tone. The diagram that you see on the screen now can represent a few things for us. The vertical axis measures amplitude, how far the string travels when set in motion, which would determine the amount of air molecules set in motion as well. The horizontal axis can represent time if we're tracking the motion of a string, or it can represent distance if we're showing wavelengths, but for our purposes, I would like it simply to represent a string, where one endpoint is the bridge and the other endpoint is the nut. And the center dashed line that runs horizontally across the grid represents the string's position when it is at rest. The green arc shows a string vibrating as a whole. And let's say for our purposes 500 cycles per second or 500 hertz. The blue arc then would show the string vibrating in half at 2 times the fundamental frequency or 1000 hertz. The orange arc shows the string vibrating in thirds at 3 times the fundamental frequency or 1500 hertz. The red arc shows the string vibrating in fourths at 4 times the fundamental frequency or 2000 hertz. The black arc shows the string vibrating in sixths, that would be 6 times the fundamental frequency, or 3000 hertz. And the teal arc would show the string vibrating in eighths at 8 times the fundamental frequency, or 4,000 hertz. The points on the arcs where they cross that central dashed line are called nodes. String players and guitar players are familiar with these points. If you lightly touch a string at a node, what you do is you would suppress the fundamental frequency, you would dampen the fundamental frequency, and you would excite the string to vibrate at the harmonic frequency of whatever node it was that you're touching. So far, we've been working in the acoustic world. Translating these principles into synthesis, the vibrating string or air column is replaced by the fluctuating voltages of the oscillator. The fluctuating voltages cause a voice coil suspended in a magnetic field to move in correlation with the voltage fluctuations. A speaker cone that is attached to the voice coil will propagate sound waves that are correlated to the voltage fluctuations. The USB PC oscilloscope will let us view the oscillator's waveform, that is the voltage fluctuations, on its oscilloscope screen, and the waveform's harmonic content on its spectrum analysis screen, so we might better understand why the three waveforms, the triangle, sawtooth, and square wave, sound differently. Let me point out, though, that though we are using Pittsburgh modular equipment for these videos, a triangle, sawtooth, or square wave in its pure form will look the same and have the same harmonic content, regardless of who manufactures the equipment. The triangle wave you see displayed on the oscilloscope screen is set at roughly 500 hertz, as all the waveforms will be during this video. The screen also tells us that this wave has a duty cycle of roughly 50%, which means that half of the waveform is spent in the positive voltage and half of the waveform is spent in the negative voltage. This actually has very little information for us when we're viewing a triangle wave and a sawtooth wave, but will become more important when we talk about square waves and pulse waves. Switching over now to the spectrum analysis screen, I've set this red marker here at 1,000 hertz, which would be the location of the second harmonic. The largest peak you see on the screen, the first one on the left, is your fundamental frequency. Notice that the second harmonic is more subdued, it's suppressed. In fact, all the even harmonics are much lower in amplitude than are the odd harmonics. This is the trademark spectral analysis for a triangle wave. Switching back to the oscilloscope screen, I'm going to gradually morph from a triangle wave to the sawtooth wave. So as the waveform changed, you should have heard quite a difference in the sound and the color and the timbre of the wave itself. Again, this is a 500 cycle wave with a 50% duty cycle, but now it has the shape of a sawtooth, and we'll switch over to the spectrum analysis screen. The red marker is still set at 1,000 hertz where the second harmonic would be. Now you can see that for the sawtooth wave, the even harmonics are much more prominent. In fact, all of the harmonics, odd and even, are represented in a very healthy fashion. This is the trademark spectrum analysis for a sawtooth wave. Now I will gradually morph, crossfade, so to speak, from the sawtooth to the square wave. Again, this is a 500 cycle, 500 hertz wave form. It has a 50% duty cycle, which means half of the time it's positive and half of the time it's negative. Now, a word about square waves and pulse waves. Just like all squares are rectangles, but not all rectangles are squares, all square waves are pulse waves, but not all pulse waves are square waves. A square wave specifically is a pulse wave that has a 50% duty cycle. That is, the pulse width is 50% positive and 50% negative. We'll see later that pulse waves with less than a 50% or greater than a 50% duty cycle sound quite different than a pure square wave. Now we'll switch over to the spectrum analysis screen. Again, the red marker is placed where the second harmonic should be. Notice that the second harmonic is absent. In fact, all even harmonics in a pure square wave are absent from the harmonic spectrum. This is what gives the square wave its hollow sound, what is described as a hollow sound. On the next screen, I will display the three spectral analyses for the square wave, the triangle wave, and the sawtooth wave stacked one above the other so we can compare their harmonic spectrums more easily. But also notice that I have plotted a dashed line across the top of the peaks of the frequency that are prominent. The slope of the sound of the square wave and the slope of the sound, the harmonic spectrum of the sawtooth wave, are relatively shallow and very similar. However, when you look at the triangle wave, which does have even harmonics, but they're less prominent than the odd harmonics, but notice how the slope of the peaks of those harmonics is much steeper than with either the square wave or the triangle wave. These are the things that we hear when we listen to the differences between the tones of the triangle wave, the square wave, and the sawtooth wave. Now I'm going to present a different way of looking at the harmonic series, and what you see on the screen now is something that may be familiar to you if you attended a music school or a conservatory when the harmonic series was presented to you. It uses a double staff system with the fundamental frequency of a low C, and then plots out the 16 harmonics as it goes up the harmonic series. What I'm going to do is I'm going to turn up the sound and start with the sawtooth wave, since it has the most harmonic content with all odd and even harmonics present at healthy amplitudes, and then I'll morph from the sawtooth to the triangle wave so that you can hear the difference in the sound, and you'll be able to see the difference in the harmonic series as well. Now, when you look at the harmonic series of the triangle wave, you can see that, yes, all of the even harmonics are still there. I've reduced the size of the note head, though, to represent the fact that they are less in amplitude than they were with the sawtooth wave. Also remember, when we looked at the plot of the curve, that the curves even of the odd harmonics, which are most prominent in the triangle wave, the slope of the amplitude was much steeper than was that of the sawtooth wave. Now I'm going to morph from the triangle wave to the square wave so that you can hear the difference in the sound, and you'll be able to see the difference in the harmonic series as well. So now looking at the square waves harmonic series, you can see all the even harmonics are absent. And notice the open spacing between the harmonics. The harmonics that are there, even though they're prominent and at a much shallower curve, similar to the sawtooth wave, the fact that the even harmonics are gone and there's absolutely no octaves present, even out to infinity, when we listen to a square wave, that is what contributes to the sound, to the hollowness, what has been described as the hollow sounding of the square wave. One last thing I'd like to touch on is pulse width modulation and its effect on the pulse wave spectrum, harmonic spectrum. Since the synthesizer block's LFO triangle wave is internally patched to the pulse width control voltage input, we can use that to see how a square wave can be modulated from a pulse wave with a less than a 50% duty cycle through a square wave to a pulse wave that has a greater than 50% duty cycle, and we'll be able to hear the difference in the sound. Now we can see on the oscilloscope screen the width of the duty cycle changing, and when I switch over to the spectrum analysis screen, you can see the even and the odd harmonics undulating back and forth as the pulse width changes. These undulations correlate to the width of the pulse wave as it modulates back and forth. And you can hear the difference in the sound as it moves from a pulse wave to a square wave. Hopefully this video has given you a better grasp on the harmonic content of the triangle, square, and sawtooth waves, and an idea how the harmonic content of the waveform translates into what you hear. Check back at the Pittsburgh Modular website for additional videos in this series.